Hey, welcome to the Chapter 6, Section 1, Functions Presentation Lecture. As we have already known, because we have used these before, there are built-in functions within Alice that we can use to better manipulate objects within our programs. We have used built-in functions in the past. You can access them by clicking on our object tree, whichever object that we want, and then clicking on the Functions tab in the Details window. Now, how does a function work? Well, a function receives a value, it's called an input value, and this performs some type of computation. So it could be greater than, less than, addition, subtraction, multiplication, division, something like that. It's going to return and send a value back. So essentially, a function is being asked to calculate something. There are different types of functions that we have used in the past. We have used a number. There's also a specific object function, color function, the Boolean function, which is coming back with a true or false answer, and then also other property values. Let's take a look at a new example. A common task in sports game programs is to bounce a ball. So you have this in basketball, soccer, many different sports. Now, to illustrate how this is done, we are going to take a ball and bounce it over what looks like a tennis net. We're going to bounce the ball over the net. The ball has to be positioned 1 meter from the net. The ball should move up and forward and then down in a forward pattern that looks something like the red drawing right here. Now it looks easy, but looks can be deceiving. The storyboard is going to be, the method is going to be titled ball over net. Do in order, toy ball is going to turn and face the net, do together, toy ball move up, toy ball move forward, then do together, ball moves down. Okay? See if we can make this work. The problem is that when we have a storyboard and we put it into code and we execute it, we might find errors. So modifications and adjustments might need to be made. Let's take a look at these two versions. Take a look at the first version, version 1. Bring that up real quick. In the wrong folder. Second. 6. All right, so here's the version 1. All over net. Here's the code. Just like we had written up in our storyboard, right? Okay, let's play it and see what happens. There's definitely a problem here, right? I mean, the ball disappears. So let's take a look at version 2 and see if the version 2 was able to fix the problem. Okay, so now we have a function in there which is going to take into consideration the height of the tennis net. Now it appears to be working properly. Okay, let's go back. Now the concept illustrated in both of these different versions is we saw that the movement of an object is sometimes relative to another object. So in this particular example, we saw that the built-in height function is used to determine the height of the net. Then the ball can move up enough to clear the net. The toy ball's up and down movements are relative to the ground. So an orient to method is used because it is not easy to tell which way is up when you're looking in a three-dimensional world. Okay, so keep that in mind, because now that we've made the ball move and appear to bounce, what about making the ball roll? Another sports game action involves rolling a ball on the ground. So we want a realistic motion rather than a slide. You want the ball to slide, and you don't want the ball to move faster than the revolutions are taking place, so it looks like it's sliding and rolling. So we got to make sure and match those two together. So we're going to call the method the realistic roll. The storyboard would be using a do together control structure, move the ball forward 1 meter, and then also have it one revolution forward. All right. Let's take a look at the toy ball roll version 1 and see how that looks. Okay, so toy ball roll version 1, here's the code. This is based off of our storyboard. Let's see what happens. Ball disappears on the ground again. So we have an issue here that needs to be resolved. What is the issue? Let's take a look. All right, our design assumes that the ball's motion is relative to the ground, but the ball turns relative to its own sense of direction. So now you actually are writing methods and have to take into consideration different objects as they move within the world. So let's take a look at version 2 and see how that is addressed. All right, so here's version 2. Now it's working great. Let's see what the code was changed. What was changed in the code to make that work correctly? Now we use as seen by the ground. And you have used this, or some of you might have used this in some of your previous exercises. I think back in chapter 2, as seen by the island when you're making the fish go around the island is probably the best way to make that one look realistic. So these different things can come up to make movements within your world look realistic. All right, so as seen by the ground can be used to make the ball turn relative to the ground rather than relative to itself. You got to keep that in mind when you're making objects move. All right, so how do we revise the approach to have the code be as concise as possible and have as minimize the steps that we have to use in order to write this code? The ball is made to roll 1 revolution. So let's suppose that we want the ball to roll a certain distance, say 3 or 4, even 10 meters along the ground. How would we do this? Will we adjust the revolutions? Or are we going to adjust the movement? How is this exactly going to work? So in order to do this, what we are going to do is we are going to take the number of revolutions, which is going to depend on the size of the ball. So the number of revolutions is going to be distance divided by p times the diameter. So now we can see already we have a calculation taking place, so we can probably start to hypothesize the fact that we are going to need to use a function here. Now, but there is no built-in function to return the number of revolutions. We are going to have to write our own. So now we are not going to be able to pull one that's already there. We are going to create our own function. Now, in order to do this, we are going to have to realize that we want to return the value computed as distance divided by pi times the diameter. Okay. Now, obviously, what is needed is the ball's diameter, which we know, and then the ball object has a built-in width function, which will allow us to calculate out, or at least call upon the diameter. The distance the ball is to travel, that can be set as a parameter to the function. So now we have this parameter again that's working its way into functions as well as methods. So how is this all going to come together? All right, well, let's take a look at the demo. We'll take a look at toy ball roll number 3. All right. Here we go, toy ball roll number 3. You hit play. That looks pretty good, right? Ball's moving as the revolutions are taking place. And it looks like it's matching up. It's not sliding at all. All right, so how do we do this? What does the code look like? So what we did is we take the toy ball, move forward 3 meters as seen by the ground for a duration of 2 seconds. We are then going to use a function, which is toy ball turned forward, and number of revolutions, which we can open here to see. Here is the revolution, or the function that we are using. We have incorporated a distance parameter into our function. So now what we have is we are going to return distance divided by pi times this toy ball's width. That's the calculation that we talked about. We can then drop that function in and put it into our method and use that calculation to execute code. Very handy trick to have in your pocket. Okay. So what you need to realize here is that concepts illustrated in this example, a function must have a return statement to send back a computed value. Now in this example, the math expression is created to compute a number or numeric value. The order of evaluation is indicated by the use of parentheses, just like any other type of math calculation or equation that you've worked on in the past, as in traditional math expressions. Now to call upon the function, we would put in, here's our function here. These are the test values. We might have to manipulate this to determine which is going to be the best for make it look as realistic as possible. We should run the animation with several test values to see which one is going to be working the best, or which one is the best expected return. What happens if you use a negative value? How how is that going to impact the possible result of this function? Well, levels, as with methods, functions can be either class level or world level. The function just presented in this example was a class level function. Now, the guidelines for class level methods also apply to class level functions, so that's going to go work hand in hand. No references to other objects, only the existing object, and no references to world level functions that you have written. Built-in world level functions are fine to use. So you got to make sure that you are writing these correctly, otherwise you will have errors that will need to be debugged. All right, so what you need to do then, if you haven't already done so, is please read Chapter 6, Section 1 on functions. Make sure that you have that taken care of and read before our next class period. And then after we have gone through our in-class example, you will be assigned the Chapter 6 lecture, the Chapter 6 lecture, which this is, and then also the lab. Okay? All right, that concludes the Chapter 6, Section 1 lab. I will see you next class period.